JavaScript's not a fast language. I think we all know and understand that. But you might be surprised about how fast JSON is, specifically JSON parse and stringify. Historically, it has been one of the best implementations of turning JSON into real objects. I mean, why wouldn't it be? It's literally JavaScript object notation. The whole point is that it's a serialized JavaScript object. Obviously, it can convert to and from. But what if I told you it just got 2 times faster? Well, I'd be lying, because it's actually close to 3 times faster in many scenarios. I am absolutely blown away with the work that the Chrome team just put in to making JSON.stringify even faster. This might seem small and simple, but there's actually a lot of fun stuff to dive into here, from the implementation of JSON.stringify to the weird quirks in V8's performance for this type of stuff, to one of my favorite fun facts, which is that many objects are easier to define, as in will be loaded faster in the VM, if you define them as JSON and then JSON.parse it, than if you actually define the object directly. There's so much fun to dive into here. I find that people just don't appreciate how much goes into JSON in order to make these simple things we rely on every day as fast as they are in the majority of use cases. Much like this change, I want to keep my video side effect free, but more importantly, I want to keep it free in general. Someone's got to cover the bill. So quick word from today's sponsor, and then we'll dive in. It's never been easier to use AI to build applications, as long as you're building small applications in small code bases. If you're trying to go big, it starts to fall apart fast. That's why today's sponsor, Augment Code, is so cool. These guys have figured out how to manage giant contexts like the thing that you're working on at your actual job. There's a lot of big companies starting to make the move, and I've even seen this myself because we've only run a couple ads with Augment, and they are regularly the #1 in our lists for the sponsor that the most of y'all like. I can't believe how positive the sentiment around them has been until I use it, and then it makes sense because it kicks so much ass. It's just so good. They recently introduced background agents, so it can open PRs for you in the cloud. With all the other things I've tried for this, I don't really trust them because if I can't run it on my machine, I don't trust that it's going to get anywhere. But since they have the context of the whole code base, unlike any other one of these tools, they are much more likely to get things right. And you can see this with how they slaughtered SWE Bench. It's the best score to date. They built something really, really good at solving hard problems with code. Companies like Uber, Lemonade, Vercel, and more are using Augment today. And honestly, I've been using it more myself for finding things in these giant code bases. If I want to figure out how something in a big open source code base works, this is how I do it. The testimonials on the homepage say it all. Augment is just a class of its own. All the other extensions don't even come close. The reliability, indexing, memory, it knows your code base really well. Wish I could use it for all eternity. Every feature in Augment feels like it was built by people who actually ship software at scale. Yeah. If you're a vibe coder, you can pass on this, but if you're building real software, check them out today at soydev.link/augment. Oh boy, I'm actually quite excited for this change. I use JSON in a lot of different places, and this should be very fun. JSON.stringify is a core JavaScript function for serializing data. I'm not even going to ask what else would you use it for because I'm not going to like the answer. If you have answers, share them and ruin my day. Its performance directly affects common operations across the web, from serializing data for a network request to saving data to local storage. Faster JSON.stringify translates to quicker page interactions and more responsive applications. That's why we're excited to share that a recent engineering effort has made JSON.stringify in V8 more than twice as fast. This post breaks down the technical optimization that made this improvement possible. Oh, we're getting our cursed use cases. This one's from the creator of Porphyr, the JSON and JavaScript wizard. Cloning objects. JSON.parse, JSON.stringify foo. Ow. It's a common pattern for deep clone. Ow. That hurts me. So remember, we want a side effect free fast path. We want something that will be really fast and not cause weird side effects. Foundation for this optimization is a new fast path that's built on a simple premise. If we can guarantee that serializing an object will not trigger any side effects, then we can use a much faster specialized implementation. A side effect in this context is anything that breaks the simple, streamlined traversal of an object. This includes not only the obvious cases, like executing user-defined code during serialization, but also more subtle internal operations that might trigger a garbage collection cycle. For details on what exactly can cause side effects and how you can avoid them, see limitations. I have a lot of thoughts on garbage collection in V8, as you might have seen in my previous video where I happened to accidentally guess correctly what the author was incorrect about and had to issue a correction on. That was fun. We'll see where this one brings me. I have a feeling this might be deeper in the weeds than I normally go, and I might seem dumb, but only one way to find out. As long as V8 can determine that serialization will be free from these side effects, it can stay on the highly optimized path. This allows it to bypass many expensive checks and defensive logic that was required by the general-purpose serializer, resulting in a significant speedup for the most common types of JavaScript objects that represent plain data. Furthermore, the new fast path is iterative. In contrast to the recursive general-purpose serializer, the architectural choice not only eliminates the need for Stack Overflow checks and allows us to quickly resume after encoding changes, but it also allows developers to serialize significantly deeper nested object graphs than were previously possible. Oh no. Oh no. I'm scared. What is the serialization depth limit? Canada Honk, I'm sure you got me an answer. How deep can you serialize your objects in V8 before you normally have problems? Crying inside. That's all I needed to hear. That is all I needed to hear. I don't need a real answer. If you have one, drop it, but I have the information I was looking for. Handling different string representations. Strings in V8 can be represented with either 1 byte or 2 byte characters. Oh god. If a string contains only ASCII characters, they are stored as a 1 byte string in V8 that uses 1 byte per character. However, if a string contains just a single character that's outside of the ASCII range, all characters on the string will now use a 2 byte representation instead, which essentially will double memory utilization. I've done a terrible thing. I now caused good old Oliver to go look at the V8 source. I'm so sorry. This is full of fun big words. To avoid the constant branching and type checks of a unified implementation, the entire stringifier is now templatized to the character type. That means we compiled 2 distinct specialized versions of the serializer, one completely optimized for 1 byte strings and another completely optimized for 2 byte strings. This does have an impact on binary size, but we think the increased performance is definitely worth it. That's very interesting, because if your JSON has an emoji in it, any optimizations for 1 byte strings aren't going to help. So instead, they compiled it twice. So there's now 2 full implementations of the serializer, one if there are no special characters and one if there are special characters. That's kind of funny. JavaScript devs will install a solution to any problem, right? The implementation handles mixed encodings efficiently. During serialization, we must already inspect each string's instance type to detect representations that we can't handle on the fast path. Like, what's conststring? Conststring class describes a string value built using the addition operator on strings. Oh, fun. You know, you can just randomly add strings together. When you do that, you now have a conststring. I'm assuming that's a constructed string. And those can have side effects. So during serialization, we must already inspect each string's instance type to detect if the representation can't be handled on the fast path. Because again, conststring might trigger garbage collection during the flattening, because if it no longer needs the previous values that you added when you made the new string, or the new string now puts you over your memory limits, the garbage collection has to come in to clean up any memory that wasn't being used before, or no longer is being used because you've defined this new value. Just for a quick example of what we're talking about here, we have the greet function. The greet function uses this const that we already defined, empty string, and then the name that you pass it. And we greet, I don't know, one of my subscribers. Speaking of which, if you haven't subbed, costs you nothing. The button's right below the video. Just click it. Helps us out. Let's imagine that instead of just console logging, we define this as message. And then we console.log message. Now, entertain me here. I know that most computers, other than like old iPhones, have enough memory to fit all of this text content totally fine. But let's say hypothetically that you ran out of memory when you added these together. When you created message by appending these, you're now over your memory limit. This would trigger a garbage collection where V8, the engine, is going to go and look for all the things that are no longer being referenced and dereference them. It can drop other values that aren't being used or definitions that aren't being hit. Since we're still in a scope where name exists, I don't think it's smart enough to let this string get cleaned up, but hypothetically it could. The point here is that the creation of this new string, in particular on consumption, because I just learned these are actually lazily evaluated, so when you define it, it's not consumed. It's when you use it that it is evaluated, at which point the garbage collection could occur. So let's go a step further, actually. We'll return message. Const sum message equals greet one of my subscribers. At this point, and again, correct me if I'm wrong, Canada Honk, because I see you in chat, you've been very helpful. This addition may not have actually been computed yet. So at this point, if I console log some message, now the computation will be completed. The string will be squeezed down together, and the name that we passed here isn't relevant anymore because this code already was executed. So this is marked for cleanup now. So when I actually use this, or in the case that we care about, const JSONified equals JSON.stringify some message, this is the point at which the addition actually happens. There are other things in this file that no longer are relevant at this point in time. We don't care anymore about this string because it's already been appended and added and calculated here. It's lazily done, but more importantly, when it's lazily done, it now has the opportunity to clean up things that don't matter anymore. So when we call this JSON.stringify, this string, which might still be in memory, now doesn't have to be anymore. But that's also kind of a side effect, which means that we have to care when we are parsing. When we do this stringifying, if it does have a side effect, which in this case it would, we now have to treat it a bit differently. Thank you again for the help. The generic term is rope strings. Very good to know. And the check they do to figure out if this is going to trigger a garbage collection or not also checks if they're going to need to use the 1-byte or the 2-byte encoding. Really convenient 2-for-1. Because of this, the decision to switch from our optimistic 1-byte stringifier to the 2-byte version is essentially free. When this existing check reveals a 2-byte string, a new 2-byte stringifier is created, inheriting the current state. At the end, the final result is constructed by simply concatenating the output from the initial 1-byte stringifier with the output of the 2-byte one. Oh, so they're making a const string too. The strategy ensures that we stay on a highly optimized path for the common case, while the transition to handling 2-byte characters is lightweight and efficient. And Canada has now done his testing. According to Oliver, they were able to get to 4,000 depth in JSON.stringify until V8 broke. I am scared to know that the limit is now higher, because if you are hitting that limit, you're doing something bad. And now you can do something bad for longer. Back to optimizing. Optimizing string serialization with SIMD. Any string in JS can contain characters that require escaping when serializing to JSON, like a quote or a backtick. A traditional character-by-character loop to find them is slow. Putting it lightly, it would be slow. To accelerate this, we employ a 2-level strategy based on the string's length. For longer strings, we switch to dedicated hardware SIMD instructions, like ARM64. This allows us to load a much larger chunk of the string into a wide SIMD register and check multiple bytes for any escape characters all at once in just a few instructions. Yes, they wrote assembly for this. FFmpeg devs are proud. Look at that. Okay, they're not actually writing assembly directly, but they're doing some very low-level C here, hitting memory registers directly. Very fun. SIMD stuff is fucking chaos. Respect to them for doing it, though. To imagine that they've done all of this optimization so people can serialize the same content 500 times in a row, up to 4,000 layers deep. Chaos. This is a good description, so I'll drop this here. Thank you, NMG. SIMD stands for Single Instruction, Multiple Data. ARM64 Neon's an implementation for ARM's SIMD instructions. Yes. As far as I know, that is true. That's all for longer strings, though. For shorter strings, where the setup cost of hardware instructions would be too high, we use a technique called SWOR, which is SIMD within a register. This approach uses clever bitwise logic on standard general-purpose registers to produce multiple characters at once with very low overhead. Oh, God. It's kind of funny that JavaScript is the most advanced language in the world, and that in many ways, JSON in V8 is more advanced and technically thorough than other full programming languages. These guys could be building Rust, and instead they're making our JSON stringify faster. It's beautiful. It's wonderful. Some of the hardest engineering work, some of the most advanced low-level optimizations that have been done in the history of software have been done to make JSON faster in V8 for Chrome. Do I know how many lines of code V8 is? I was just asked by Canada Honk, and I am scared to know. This is a fun fact that you just have ready to go, don't you? I'm about to feel sick. Just drop the number. 1.6 million. So we have 2x more NPM packages than we have lines of code in V8, but the fact that those are somewhat close is really funny. And JSC is 800K as well. Fucking Christ. The bundle for V8 is 9 megabytes. That's like the compiled source comes out to 9 megs. God. Apparently, if you include comments, additional code, tests, and everything, total lines are almost 3 million. Some information's better not known. That hurts me. Hey, at least we can serialize our fucking JavaScript objects faster now. Regardless of the method, the process is highly efficient. We rapidly scan through the string chunk by chunk. If no chunks contain any special characters, which is the common case, we can simply copy the whole string. And now there's the express lane on the fast path, continuing to optimize further. Even within the main fast path, we found the opportunity for another, even faster express lane. By default, the fast path must iterate over an object's properties and, for each key, perform a series of checks. Confirm that the key is not a symbol, ensure it's enumerable, and finally, scan the string for characters that require escaping. To eliminate this, we introduce a flag on an object's hidden class. Once we have serialized all properties of an object, we mark its hidden class as fast JSON iterable if no property key is a symbol. All properties are now enumerable, and no property key contains characters that require escaping. Cool. Gotta love those hidden classes in V8. There's a lot of these implementation details that we don't necessarily have access to in the JavaScript layer that we're in, but they're in there so that V8 could do optimizations. V8 could do without hidden classes, sure. It would treat each object as a bag of properties. However, a very useful principle would have been left laying around, the principle of intelligent design. So they're literally saying it would be unintelligent to not have hidden classes. V8 surmises that you'll only create so many different kinds of objects, and each kind of object will be used in what can eventually be seen to be a stereotypical way. I say eventually be seen because the JavaScript language is a scripting language, not a precompiled one. So V8 never knows what will come next. So what this does is if you have an object shape that you use multiple times, V8 will notice and create a struct for that it can use to know and identify this shape of object to map it and use it more efficiently. So here we have a function, but in this function we use this, which you should never do, but you can do. And if the extra data is not a number, then we put it in experience. Otherwise, we put it in prominence. Very interesting. So we have these two things that we call by calling new peak that both have name and height, but then this one has prominence because we put a number, and then this one has experience because we put a string. With this code, we've already got an interesting map tree from the root map, also known as the initial map, which is attached to the function peak. So we map it with name, we then map it with height, and now with prominence and experience, we have two different mappings. Each blue box is a map, starting with the initial one. This is the map of objects returned if somehow we manage to run the function peak without adding a single property. The follow-up maps are the ones that result by adding the properties given by the names on the edges between maps. Each map has a list of the properties associated with an object of the map. And if you're wondering why there's stops for all of these, it's because when the function runs, none of the properties are defined yet. Just the function running. So it starts with no values attached to this, and then it has name. So now we have a version with nothing and a version with name. Now we have a third version with height, and now we have a fourth or a fifth version. It can't be both. It's one or the other depending on this condition. Those are the maps. Not like map KV store, but map the mappings of the different keys that can exist in these shapes. From one of these maps, say map 3, which is the hidden class of the object that you'll get if you pass a number from the extra argument in peak. You can follow a backlink up all the way to the initial map. Let's try it again with the extra information. Interesting. So the key here is that the object field locations are mapped at a lower level so that it can figure out when you ask for a certain key where that is in memory faster. So the name gets key I0, height gets key I1, and then prominence or experience get keys I2. Apparently, you have to create 7 objects in order for it to complete the mapping. And once you've done that, your peak objects will have exactly 3 in-object properties with no possibility to add more directly in the object. Any additional properties will be offloaded to the object's property backing store. It's just an array of property values whose index comes from the map. Well, technically the descriptor array, yeah. So if you then add an additional value like m2.cost, this will create a new mapping that has cost as a constant on this general key. Again, it does this so that when you have a common shape for an object, it can map the key to the place it's stored in memory way faster. But when you have uncommon parts appended to the shape, like in this case, cost, that's going to be a little more expensive a lookup, but not annoyingly enough so to cause real problems. I am sure that my attempt to explain this is triggering Oliver quite a bit. I'm doing my best. Let me know if I make any factual errors. I have so many fun facts about V8, I can hurt brains in seconds. I can't even imagine. Pretty good. Okay, we're doing well. Well, let me ruin it really quick. Somebody mentioned ducks, and I can do that. We all love animals for our classes and object definitions, right? Ducks have names, they have heights, they have weights or legs or whatever. You can think of this cost field, this new P0 appended field, almost like a shirt it's wearing. It's not part of the duck, but we have given it to the duck, so now it is there with the duck. But when you're trying to analyze the duck, this is now more expensive than just counting the number of feet. We now vaguely understand hidden classes in JS, and specifically in V8. When we serialize an object that is the same hidden class as an object that we serialized before, which is quite common, like in an array of objects where they all have the same shape. That makes a ton of sense. If you're trying to serialize a user array that has a bunch of users all of the same type, we've found the hidden class and know how it serializes after the first one. So we can use that serialization awareness to not have to recompute for everything else in this array. So if we know that, and it's a fast JSON iterable class, we can now simply copy all the keys to the string buffer without any further checks. That's pretty cool, because again, we know the memory location for each of these fields. So if we also know that in map 3 or 4, we don't have to do any special stuff because we don't have to worry about garbage collection or side effects, then we don't have to care at all. We can literally just rip from those memory locations straight into our new string. Really cool. We also added this optimization to JSON.parse, where we can utilize it for fast key comparisons while parsing an array, assuming that objects in the array often have the same hidden classes. That is huge, and I will use that to tangent over to one of my favorite fun facts in JavaScript and V8, which is the fact, this isn't disputed, this is real, that in many cases, it is faster to define an object by passing it as a string to JSON parse than it would be to just define the object in line. One of my favorite key quirks in the language and engine that we spend all our time working within. Because the JSON grammar is much simpler than JavaScript's grammar, JSON can be parsed more efficiently than JS can. This knowledge can be applied to improve startup performance for web apps that ship large JSON-like configuration object literals, like an inline Redux store. Instead of inlining like so, you can put it in JSON instead. Do you understand how chaotic that is? And that they brought up Redux as the example? If you have a complex object that is the starting point for your application with a lot of different keys, maybe some crazy arrays and all these other things, JavaScript has so many things to parse that it will actually be slower than JSON because, again, it's a limited grammar. There's only so many types in JSON. There's really like 3. You got strings, you got numbers, you got objects, and I guess you got Booleans. So it's actually very efficient to parse JSON. And now it's even faster because they found ways to remap and reuse memory locations and registers based on the hidden classes of the things you are serializing and deserializing. And to be very clear, it would be hard for these to be the things that are making your app slower. But if you are the type that wants to optimize every single corner, you probably already learned this just by going through the profiler in Chrome. But you're seeing real time being spent on like allocating a value. Maybe try doing it in JSON, see what happens. Back to these new optimizations. A faster double to string algorithm. Converting numbers to their string representation is a surprisingly complex and performance critical task. As part of our work on JSON.stringify, we identified an opportunity to significantly speed up the process by upgrading our core double to string algorithm. We've now replaced the long-serving Grisou3 algorithm with DragonBox for shortest length number to string conversions. It's kind of crazy to think that the way you turn a number into a string is so complex that there have been lots of different implementations, and we have finally moved to a new one after however many fucking decades V8's been around for. This is a reference implementation of DragonBox, which is a theoretical fucking piece of research on how to convert floating point binary decimal to strings. This is hilarious that there are like whole ass research papers about how to turn a number into a string as efficiently as possible. And this is an implementation of that in C++ that has now made its way into V8 so that your numbers will convert to strings faster when you JSON.stringify. I know about Asm.js. I remember these days, the original WebAssembly. I think I'm slightly older than you, so I was there when this happened. It was a whole moment. We do not want to revive Asm.js. WASM is the correct solution. We shouldn't be making assembly work in JS. We should be making something that works like assembly in the web. You're 20. God damn it. I forget how young you are. Jesus. Your wisdom is far too great for your mere 20 years mortal shell. Yeah, you know too much. While the optimization was driven by our JSON.stringify profiling, the new DragonBox implementation benefits all calls to number.prototype.toString throughout V8. So if your app is slow because you were calling toString on numbers too often, it might be less slow now. Cool. This means any code that converts numbers to strings, not just JSON serialization, will see this performance boost as well. Awesome. And even more optimization. Optimizing the underlying temporary buffer. A significant source of overhead in any string building operation is how memory is managed. Previously, our stringifier built the output in a single contiguous buffer in the C++ heap. While simple, this approach has a significant drawback. Whenever the buffer ran out of space, we had to allocate a larger one and copy the entire existing content over. For large JSON objects, the cycle of reallocation and copying created major performance overhead. Interesting. Again, buffer overflows are a huge concern when your engine just spits out shit all of the time and you have to garbage collect whenever you get a chance to. The crucial insight was that forcing this temporary buffer to be contiguous offered no real benefit, as the final result is assembled into a single string only at the very end. With this in mind, we replaced the old system with a segmented buffer. Instead of putting everything into a single large growing block of memory, we now use a list of smaller buffers, or segments, allocated in the V8 zone memory. When a segment is full, we simply allocate a new one and continue writing there, which completely eliminates the expensive copy operations. That's really cool. You'd be surprised how many of these realizations have powered significant innovations in software. They're like, oh, we're storing all this in one place. We don't use it all till the end. What if we just store it wherever and add it together at the end anyways? Another really good point from Canada Honk. The scary thing here is that if there's a one-line mistake in any of that code, in theory, with sandbox escapes, it could cause RCEs for parsing JSON. Terrifying. Actually terrifying. I am very thankful that this wasn't vibe coded. Let's try something funny. Gonna intentionally not give GPT-5 access to the internet. I'm not giving it search. I'm gonna ask it, what are some theoretical ways we can improve the performance of JSON.stringify side of the V8 engine? Assume we have the ability to make any change we want to V8's source code. We'll see what that comes up with. Curious what GPT-5 has to say. What would it look like to vibe code these optimizations? I have to know. And while we wait for that, let's talk about limitations. The new fast path achieves its speed by specializing for common and simple cases. If the data being serialized doesn't meet these criteria, then V8 will fall back to the general purpose serializer to ensure correctness. To get the full performance benefit, the JSON.stringify call must adhere to the following conditions. No replacer or space arguments. Providing a replacer function or a space or gap argument for pretty printing are features handled exclusively by the general purpose path. Fun. So if you're doing all the fancy things that JSON.stringify has the opportunity to make the output look nicer, it opts out of the speed. Makes sense. Plain data objects and arrays. The objects being serialized should be simple data containers. This means that they, and any of their prototypes, must not have a custom .to.json method. If you're defining your own to.json, you're deeper than we are. Good, cool, have fun. But it can't do any of these memory allocation level changes. It can't just read a register and know what to do with it if you have a custom to.json. Makes sense. More reason to not write custom bullshit if you don't need to. The fast path assumes standard prototypes like object.prototype or array.prototype that don't have custom serialization logic. And if this is how you learned that you can override the .to.json, don't do it. Don't put yourself through this. It's not worth it. I've done some terrible things with that function. Don't do it. Trust me. And I hope you never learn that you can override what happens when you add two things together. Danger awaits. Be very careful, traveler. No indexed properties on objects. The fast path is optimized for objects with regular string-based keys. If an object contains array-like index properties, like 0, 1, etc., it will be handled by the slower and more general serializer. And more reason to not use objects as though they're arrays. Let an object be an object. And we have simple string types. Some internal V8 string representations, like const string, can require memory allocation to be flattened before they can be serialized. The fast path avoids any operation that might trigger such allocations and works best with simple sequential strings. This is something that's hard to influence as a web developer, but don't worry, it should just work in most cases. For the vast majority of use cases, such as serializing data for API responses or caching configuration objects, these conditions are naturally met, which allows developers to benefit from the performance improvements automatically. Here's how GPT-5, in T3 chat by the way, thinks we could theoretically optimize this. Let's see if it got any of these things. Look at that, it's actually guessing some of the things. If objects are composed exclusively of data properties, they have a stable map and hidden classes, and no dictionary mode and no elements that imply holes. Keep non-ASCII unescaped as spec allows, or maximum throughput. And if any guard fails, de-op to the existing general path. Shape-based property plan. For objects with the same map, precompile a stable list of property fields in enumeration order and serialize by directly reading the fields, skipping generic property key collection. Did they train on the plan for this? This is spot on. If serializing an array when the elements share a map, hoist and reuse the property plan across elements. This is the iterating over an array thing that we talked about too. It's guessing all this pretty well. Oh look, they even included the SIMD vectorized ASCII scan. That's hilarious. The 2-tier string path, one for the 1-byte strings and one for the 2-byte strings. It got most of this. Turns out we could have vibe coded the performance win on string serialization in V8. Who would have thought? I wouldn't have. I absolutely would not have thought that we could vibe code this. And to be clear, we can't vibe code this. But it's pretty cool that you can get most of the answer like this. That's very, very cool. And now let's look at the results. Beautiful. Why does the Pixel 9 serialize a string faster than the M1 Mac does? That hurts me. I should actually read the conclusion, though. By rethinking JSON.stringify from the ground up, from its high-level logic down to its core memory and character handling operations, we've delivered a more than 2x performance improvement measured on the Jetstream 2 JSON.stringify inspector bench. See the figures below. These optimizations are now available in V8 starting with version 13.8, which is Chrome 138. Oh, scores, not times. Thank you. Appreciate the correction, Naman. Because the benchmark isn't a time benchmark, it's a score bench. So we actually want the bar to be higher. Mac users, stay winning. We'll take it. This was awesome. This was an actually really good write-up that makes this information digestible. And this is not info that should be digestible. Huge shout out to Patrick for writing this, as well as a shout out to Oliver for all their help making sure I didn't get information wrong on this. They're one of the smartest JS Engine people ever, just period. Lots of things I talk about with JavaScript are information that I got pretty directly from Oliver. Great resource. Love him to death. Definitely somebody you should follow if you want to keep track of their utter madness with the JavaScript engine. I guess it's time to make like JSON Stringify and get out of here really quick. Bye, nerds.